Okay, so Superfluidity. Superfluidity is a European research project. It's focusing on 5G mobile networks with the angle of open source, and that's what we're going to cover today. Let's get started. So we're going to talk generally about what is a research project for the EU, for the European Union. And then we'll talk obviously about Superfluidity. We'll deep dive into some of the architecture and solutions we provided for the NFV domain. We'll talk specifically about Red Hat contribution because it's a huge project. We'll see that later on. We'll try to cover some more aspects and future work that we're looking to do.
I hope everyone had a good lunch.
So first of all, what is the European Union research project? Specifically, we can talk about Horizon 2020. How many people here have heard about Horizon 2020? Just two. That's pretty amazing, given the fact that it is sponsored for almost 80 billion euros. So it's a lot of money. It's a lot of money that is being put into innovation and research. And this is a way for the European Union to support the research work that is being done. The way it works is that this program includes multiple projects. Each project is spent over typically 2 to 3 years. Superfluidity is one of these projects. And the program, generally, the money that we got is for almost 7 years. So there are multiple projects that you can choose, or you can submit if you are someone who's interested in doing research. It's a good base for collaboration. So why the European Union put so much money into it? It's a good place to find collaboration between the private sector and the public sector. So you can easily find companies, small startups, working alongside with huge companies like IBM, Intel, Red Hat. And basically, that's a good space where they can collaborate and share knowledge without all the proprietary work that is being done usually in startups. Another good thing that comes out of this research is usually the collaboration between the academia and the industry, which is it's something that both sides need, because as you can imagine, the academia is looking for someone to be more practical and to use the result of the research. And sometimes there are issues or problems we find in the industry that we need the academia to research and look ahead and see how this is sorted out. So the money for Horizon 2020 is spent across multiple domains. We're going to talk about NFV today, but it covers also Internet of Things, green energy, autonomous cars, so plenty of topics that can be submitted as a project. Okay, so Superfluidity is one of these projects. It is a project that is a collaboration of 18 partners we're going to cover for them, and it is about the NFV domain. So what challenges did we find? When you submit a research project, basically you have to be aware of what is the domain you're tackling and what are the big issues that exist in this domain, and which one of them you want to tackle in your research, obviously. So covering in high level, what are the NFV challenges? I'm sure you guys all heard to some extent about some of them. So we'll go over them very quickly. So long provisioning time. The telco companies and the telco industry has been going through major changes in the past 5 years. Obviously, it's been going through a lot of changes for the past decade, but you can see in the last 5 years, the way we use cellular networks, the way we consume the cellular traffic, everybody's using video streaming, the amount of traffic that is going through the cellular networks has increased dramatically in the past 5 years. And we need to deal with that. So when you want to roll out a new service, basically, today it takes days to weeks in a cellular network. What we're looking for is to be able to deploy a new service within seconds, minutes. If we're talking about hours, it's almost not acceptable in the future. So this is one of the domains we had to tackle. The next thing is over-provisioning of hardware. Obviously, today, telco companies are looking at the peak hours, So when it's a holiday or an unfortunate terror attack, you can see a peak in the cellular networks, and this is the amount of hardware they have to be able to deal with those peaks. So they have to buy a lot of hardware that is idled most of the time. That's very wasteful. One other thing is that they need to buy services. Today they buy black box services. Usually it comes like a sealed box with the software inside, and all they do is like plug it into their networks, into data centers. They don't have any visibility into what is in the box. If something is broken, they just buy another box. If they want to scale out, they have to buy another box. And everything is vendor locked in. So if you want to buy a service from one provider and the other day move to a different provider, either you buy everything from scratch or you stuck with your original provider. So these are some of the big issues that they have in the NFV domain. And in Superfluidity, we started a project 2 years ago, actually. It started in July 2015. And when we started looking at it, we said, OK, obviously we can't solve everything. But what do we want to focus on? We chose to focus on some use cases that actually we found to be the most interesting. So one of the things that is obvious that is going to change with the way we use the cellular networks is that we need compute resources closer to the mobile devices. So what happens today is when you guys use your cell phone, each packet is going all the way to the back to the core network of the cellular data centers. So they have a local antenna, usually within 2 kilometers from where you stand. And then there's the processing of the packet, but handling the packet goes all the way back. This is unacceptable for the future use cases. So one of the use cases we have that we tackle in the project is video streaming. So we were talking about having people in a stadium, in a football stadium. They are all watching a game, but while watching the game, what the companies want is to have live streaming of additional data, what they call metadata, on the game. So you have 3,000 people or more, in the US it's much more, that are connected to your local cellular antenna, and they are all video streaming at the same time. And now imagine that these packets are going all the way back to the core network and back to the mobile devices. That's not something they can bear from two perspectives. One, the amount of traffic that it generates is something that is wasteful because a lot of the data is duplicated, as you can imagine. And also, the delay is horrible. So these two things are not handleable, are not manageable going forward with the current infrastructure. So what we were looking for is actually to be able to mitigate these issues. So we'll see what we did for this. The second objective is actually driven from the first one. So once we found a way to have compute resources close to the mobile devices, then the next thing is that the telco companies can have new business model and can utilize things in a different way. So as you're going to see, some of the consortium members are telco companies, and they were explicitly looking for solutions that would enable them to monetize on the services. Yes, and the last thing is obviously reduce costs. So nothing goes without reducing costs. That's the motivation for most of the research we're doing today in the NFV domain. OK. So looking at the consortium, it includes 18 partners. Some of them are from the academia. Big universities, one of them is from Italy, and we have from Lodz and from Bucharest, Ben Gurion, obviously our university from Israel. There's telco operators, British Telecom, Telefonica, what used to be Portugal Telecom, and the industry, which is Nokia, NEC, Red Hat. So you can see the partnership is huge. So there are so many people, so many contributors. The project is huge. We'll see some of the things we did, but definitely there's a lot more. OK, so now that we have understand the domain, let's see what was the vision. What we're aiming for in Superfluidity is the ability to instantiate services on the fly. So when you have a mobile device and we identify a specific packet or something, we can start an application that is going to be the answer, kind of, for this packet. So we want to instantiate services on the fly. We want to run them everywhere, anywhere. Obviously, we're talking about the edge, which is close to the mobile device, but we want to be able to run services also in the core network. Maybe everything has to be connected. We're going back to the networking infrastructure. And then one additional challenge is that we want to shift them transparently. You take your mobile device and you drive from one place to another. And from your perspective, you don't care if the antenna changed, right? So if you had a service that you got from a specific, let's say, edge, right? Then you move to another edge, you expect to get the same service. You don't expect the internet to disconnect or anything, right? So these are the things we wanted to look into. And that's how we started. So we're going to look quickly on some of the changes that already happened in NFV. So one of them is the blue box. We started with a black box that with software, proprietary software. That's how the data center looked like. And then, obviously, the first evolution that was done is virtualization, right? This is already, well, not done, but it's in the it made a lot of progress in the past 2 years. A lot of the NFV functions are already virtual machines, all containers, as we're going to see, on off-the-shelf hardware. The next step of the evolution was to take the virtualization and actually split it into control plane and data plane. A lot of the functionality of the control plane just went into the SDN controller. So we already saved a lot of the management applications that we needed. Basically, this, in general, makes it more consumable, detached from the proprietary hardware, and theoretically, in the long run, it is supposed to save money, obviously, because upgrades would be easier, rolling out of services would be shorter, etc. Okay, the next change that happened is that today we use LTE is like the latest technology in telco. So we had 3G, 4G, etc. So LTE is the latest. So you have the remote radio head, which is the antenna that gets all the signals from your mobile. And then there's the baseband unit, which translates, among other things, it translates the signal from analogical signal to digital, does some basic processing, and then sends the packets back to the core. The change that we're looking for at 5G, which is the next generation, is basically do the separation between the radio and the baseband. So having the radio every 2 kilometers or so is kind of basic. There's no way around this. But then the BBU can be aggregated into hubs. So you can at least, to some extent, gather together some of the computation. It's not the whole computation, but at least this is what we will later call the C-run. So you can see here the aggregation. There is a physical limitation on the connection between the antenna and the BBU. It can be up to 2 kilometers, I think, or so. So the hub is limited. You can't aggregate all the antennas, but at least some of them. So this is also known as the C-run. And then the next step of the evolution, which is something we're going to focus on, is the computation resources. So we were saying we need computation resources next to the edge. And basically what we did here is we already have some kind of a local data center, right? So why not extend it to also be able to run some cloud applications? So that's the next step of the evolution. So having the C-run together with the mobile edge computing. Now it's also known as the multi-network edge computing, because it's apparently a problem that applies not only to the cellular domain. So what we have here is basically a cloud. like we're all familiar with. It's just a small cloud. And you can see here the traffic offload filter. So basically, when a packet comes, we make a decision per packet. Do we need to send it all the way to the core? Or can we handle it in this new application resources, new computational resources that we have? So that's the differentiation, and that's the big change that the 5G is bringing to the picture. So you have a way to compute stuff locally. The next focus that we're going to discuss is actually which type of applications are running in this cloud, and is it only virtual machine, and how do we make sure the infrastructure can support all of this? Can you ask again, please? Yes, so basically we're saying it won't be a base station. There will be a base station hub, a CRAN, which is an aggregation of a few base stations, and there would be a cloud in there, a limited cloud, so it won't have like 10,000 of racks. And this is actually one of the problems we had to deal with. It's limited in resources. So we're talking about 10 to 20 servers because it's local and it's distributed. So in terms of, one of the challenges that we have here is how we make sure the footprint of the management is very small, right? If you have 10 servers, you don't want to use 9 of them to be able to manage the one server, right? So this is definitely one of the challenges. Okay, yeah, so the proprietary hardware is still stuck here. We have no other choice. You're right. So even here, there is a research project in the European Union that talks about virtualizations of this functionality as well, as amazing as it sounds. So it's not easy, but there is a research project being worked on. In the baseband, we already virtualized everything. So you have the custom hardware that is running some basic functionality and basic applications. And yes, this is, so we're going to discuss it because it's not really a virtual machine. Here we had to have containers. We're going to cover that in a few slides, okay? Yes, so that's the amazing part. Okay, so the question is, can we run OpenStack in the edge cloud? The answer is yes. So there are many ways you can deploy OpenStack. Basically, OpenStack is a collection of components. The way you choose to manage it, the way you choose to deploy it, there are many ways. You can do it in different ways. So we found a way. Obviously, you have to pay for small footprint, right? So you can't have HA with 3 network nodes, with 3 storage nodes, and still run it on the cloud. So you have to pay with something. So maybe in some cases you can say that high availability of something is not as crucial as something else. So instead of 3 instances of the API, you would have only 2. So you do have to pay, but you can get to a very low footprint that still makes this worthwhile. We have a POC that is working and is pretty awesome, so we'll see. Okay, so this is the big picture. I'll try to go over it really fast because we covered most of it. There's the cell, the physical cell. There's the local data center. The cell is every 2 kilometers or so. The local data center, you have a couple of them per city. So here you have both the CRAN and the MEC, the mobile edge computing, running with the local computational resource. Then you have the regional data center, which is usually a couple of them per country. And then you have the central data center, which is 1 or 2 or a few per continent. So it's a hierarchical structure. And I think we can move to the next slides because we actually want to talk about the solutions. Okay, so now we have to choose which technologies we want to use to run this. Well, this is specifically for the edge cloud and also for the orchestration. We need to manage. I'll start with this slide. So we need to manage a couple of them, right? We have the CRAN and the MEC. This is the edge cloud, but one is not enough. So we need a few more, and we need a way to manage them in an efficient way. There's obviously also the core data center that we we can't forget about, because this is also part of the network. In some cases, you need connectivity. So the question was, which tool can we use to be able to run everything? So then we looked at the applications. Some of the applications are virtual machines. And we actually, to be honest, 2 years ago, we started only with virtual machines. Everything, at least the plan was to virtualize everything, get everything running, and then have the MEC with OpenStack and virtual machines. Very fast, we got to the conclusion that at least for the C-run workload, the virtual machine is not good enough. They need boot time, which is microseconds or milliseconds. They need to be huge density. So one of the issues that we were talking about is the low footprint, right? So we only have 10 servers. We can't afford running everything on a virtual machine. The cost is very high. So at least some of it, we would need to use the density that containers enable us, and we actually moved to containerization. Some of them are very sensitive to performance, so we had to run them on bare metal. So it's not only it's containers, then even Kubernetes might not be relevant in some cases, so just like bare metal with containers, especially when we're talking about packet processing with huge volume. There could be any solution. The question was, do we have to use Kubernetes? The answer is no. Do we have to use OpenStack? The answer is no. What we chose in this project is to adopt specifically Kubernetes for the containers and OpenStack for the virtual machines. And one of the reasons is that we also have the bridging in terms of networking between the two. And we use Courier, which we're going to discuss in a second, how we actually made one networking infrastructure for both stacks. And yeah, you can see in the picture also the Open Daylight, which is the control, the SDN controller. For some cases, it's very useful, Open Daylight, but in our demo, in our first demo, we were not able to get to the point where we actually have SDN controller. But this is the plan. Like, we have 6 months to the next demo, and we really hope we'll be able to integrate also Open Daylight. Okay, and one more technology that is worth mentioning is ManageIQ. ManageIQ is a management application. We're going to see what contribution we did, but the interesting part is that ManageIQ is able to manage your virtual machines and your containers and your networking resources. So we had a single management application that actually gave us visibility to everything. And that is something that was hard to find, at least in the open source domain. And that gave us a lot of the functionality that we were missing. So we're going to cover it in the next slide. OK, 2 slides. So as I said, we have 18 partners. A lot of contribution went into the work that was done. But obviously, I'm from Red Hat, and I'm more familiar with the work that we did in Red Hat, so I'll be happy to share with you some of the things that we did. So the first year we started, well, the first use case we had is to have deployment of virtual machines with video streaming, and then migrate one of the virtual machines to another edge. That was the first use case. And when we started, the first thing we saw is that once you start the video streaming, one of the VM just took over the bandwidth. The other VMs were, there was a starvation for some of the VMs. They didn't get the quality of service they were looking for. So the first contribution we did is to add to Neutron the quality of service API and implementation for the ML2 OVS agent. So that was 2 years ago almost. And then we had another issue. Again, while just walking our ways to the basic scenarios, we found that there is some performance issue when you add actually some ACLs for the VM. If you want to add some kind of security group, using OpenStack terminology, the performance degrades. We couldn't find out, like, at the beginning, we didn't know why. Looking into the details, we found that the implementation that used to use Linux Bridge and IP tables was pretty bad. So what we did is we developed the OVS firewall. It's available today. It is based on contract D. You can find it. I think that in the next, at least the vision is that in the next version that will be the default. But even if it's not, then you can just configure it and use it today. We definitely saw the performance gain that we got out of this. So that was the second contribution that we did. Okay, so the question is, how is this correspond to OVN? 2 years ago, OVN was not a thing, right? So it's a big thing now, but we do not use that in our project. We use ML2 OVS, which is the reference implementation, the default implementation in upstream, and that's what we were focusing on. And also the implementation in contract was not available 2 years ago, so it didn't apply even to OVN. Okay, so that was the first year, and now the second year. In the second year, we focused on two things. One of them is Kuryr. We're going to get into details in a second. The second one is basically ManageIQ. So these are the two things we invested in. Let's start with Kuryr because it's awesome. So first of all, Kuryr, for those of you who do not know, it's a project in OpenStack. It's the bridging infrastructure between, let's say, the networking of Kubernetes to networking in OpenStack. Actually, the founders of these projects are, some of them are Israelis, and we have Gal Sagi here. You can raise your hand. He's one of the people who started the project. We have Tony. Tony is also here. He's the PTL of Kuryr. So Tony is also one of the founders. So a good bunch of people started a great idea to get the networking. We've got all the experience in networking abstraction in OpenStack. We've been working on this for, I don't know how many years. It's like 5 or 6 years with different vendors. We have tons of experience. Why not leverage that in the domain where it lacks a lot of experience? In containers, the way networking is done is not standardized. There's no single API. I'm sure everyone knows that, right? So Kuryr is basically a way to leverage what we already did. So we used Kuryr to be able to use one networking infrastructure between containers and virtual machines. And there are two ways to deploy. One of them is when you use side-by-side deployment. So some of the servers are used for containers, others for virtual machines. That's one way. Another way, which is more common today in the mobile world, but also outside of the mobile world, is to run containers on top of virtual machines. So you start virtual machines, and on top of that, you start containers. And the reason for that, security. First of all, this is one of the vulnerabilities of containers, and this is one of the ways to work around it. Obviously, you still gain a lot in terms of density. You still gain a lot of the benefits that you get from containers because you just start them on virtual machines. So you kind of get good from both worlds. It doesn't apply for all use cases, but it does for our use case. So the first thing we contributed to Kuryr is added the support for VLAN trunk. For those of you who are not familiar with it, VLAN trunk is basically an enabler. Is an enabler to use containers within virtual machines. The second contribution that is being done today is actually adding support for port pools changes. So you can see here two diagrams. So this is the boot time, the blue line is the boot time before adding port pools, and the red is after. And the concept is very basic. So you have a pool of ports, and you just take them from the pool instead of creating them when you start a new pod. You can see the major improvement. And somebody just told me that I have 1 minute, so we're not going to go into the details. Just mentioning this very quickly, we talked about ManageIQ, the big or the huge advantage it gives you. It gives you a single platform to manage everything. So you can manage the different edge, the different CRAN, the containers, the virtual machines, etc. We contributed some work into ManageIQ, and if you're interested, I'll be happy to give you the details after the session. Okay, to wrap up, there are also other contributors to Superfluidity. Other big companies did a lot of awesome things. a lot of work being done in the academia. One of the best papers in 2016 was around split docks and quick click. So it's a virtual router that is amazing with performance. There's a security framework, SIMnet. Sorry, SIMnet that was contributed, additional work for Kuryr, and some other great things that were done. So all of this is sponsored by the European Union in the context of Horizon 2020, which is what we discussed. Basically, the focus for the project going forward is to keep on supporting open source, adopting open source infrastructure, and closing gaps in the open source solution where it's available. So this is something we're going to work on for the next 6 months as well. And hopefully we'll have additional demos that we can share. It's all publicly available in the internet and in superfluidity.eu. So thank you, everyone. I don't know, I don't have time for questions.